Okay. I wanted to do a video on the basic idea of integral relationships. Um, it's not going to be as in detail as we did in class, but that's okay. So, the basic idea is that we're talking about systems, right? And systems are a defined mass. There's a certain amount of mass that I've said, this is my system. The key here is mass. And we can say that there are extensive properties of that system, which we could call B system, which is some property of the system, like an extensive property that is conserved. So with things like, this could be energy, momentum, it could be mass itself, all right, enthalpy, dot, dot, dot. The list goes on, all right? And importantly, one of the things we could say is we could think about beta, which is just this B system, dB system, dm, okay? All right, so the basic idea is in fluids, when we're dealing with fluids, it's a lot easier for us to think about a control volume, all right? And that control volume could be in some sort of flow field, like this, all right? And what we could think about is at some time t, we could have a mass in that control volume that exactly lined up, right, with our control volume. All right, and then at some time t plus dt, the mass and the control volume would no longer be aligned because of flow. All right, there's my control volume and my mass now. Right, these are not great pictures, I'm aware. Looks like this, right? And so the question is, how does B of my system relate to B of my control volume? Okay, that's the question. That's what we're after. All right. So first of all, we can think about this. At time t, B of my system should equal B of my control volume, right? And we can also say that in general, B of my control volume should equal the integral over the volume, my control volume, of beta rho dV. All right? Now, when I said up here that my system's property was conserved, what that means is there's some law that tells me what happens with dB dt of my system. All right, there's some law that conserves that, okay? So what I want to know is what is dB system dt, which is roughly B of my system at t plus dt minus B of my system at t over dt, all right? How is that related to the control volume? Well, this is actually kind of, in some ways, easy. This value here, right, we've already said this equals B of my control volume at t. But what about B of my system at t plus dt? What about this? So let's go back to our last slide for a second. If we look at this slide, at time t, there's this area here where the control volume and the system overlap. There's this area here of B in the system that has left, it has flown out, and then there's this area here of new stuff that has come into my control volume. So when I think about this B of my system at t dt, right, I can say that the B of my system at t plus dt is equal to B of my control volume at t plus dt, right, minus the stuff that has flown into my system, and I'm sorry, into my control volume, plus the stuff that has left my control volume, plus the stuff that is left. All right. So if we rewrite our equation up here, I get this. All right, and so, okay. The question is, what are these? how do I find these? So let's just think about a little section of our control volume here, and we'll call it dA, okay? And dA is going to have some normal vector to it, n, that defines the outward direction. And at dA, there's going to be also some velocity, right? That's carrying my fluid out, all right? And if I think about this, over that time period t plus delta t, right, my system has moved out some amount here, some height h, and here's this beta and here's the beta that's left, okay? And so the question is, what is this little section of dB out equal? dB out would equal beta times the mass that's left, and that equals beta times rho times the volume that's left, and that equals beta times rho times h times the area that's left, right? Now h is equal to v normal, which is the velocity in the normal direction, times dt, and this is equal to v dot n, all right? Which means if we take all of this, we get that we have beta rho v dot n dA. Now, if I integrate this all the way around, I would get B out equals the integral over my control surface of beta rho v dot n dA, and I get something very similar for Bn. Beta rho v dot n dA, where I was just thinking over my control surfaces out and my control surfaces in. All right. But this would also need to be times multiply. This would be B dot, right? So in order to make these work, all right, I would say times dt, and I would integrate over all times, right? So at some time dt, so let me just write it out on the next slide. In order for this to really work, then Bn equals dt times B dot in. That's what I just calculated. And B out equals dt times B dot out. All right, now if I go back to my original equation and plug everything in, I get that dB system dt is going to equal B of my control volume at t plus dt minus B of my control volume at t over dt plus the integral over my control surfaces out of beta rho v dot n dA minus the integral over my control surfaces in beta rho v dot n dA. This is just the volume in my control, and this is just dB control volume dt. And so I can rewrite this whole thing as d dt, the integral over my control volume rho beta dV, right? That's how much there is in there. Plus, and I can rewrite this as a single integral because the v dot n covers the pluses and minuses. I'll show you that in 1 second. What I mean by that is this: if this is my control surface here, and here's my velocity, here's my normal, and here's my velocity, then v dot n at an outlet is going to be a positive value. This is my control surface here, and here's my normal, and it's this is an inlet, and my normal would point out at an inlet, and here's my velocity coming in, then v dot n will equal negative, and so I'm covered. All right, now it's important to note that if v is a function of, is not constant, right, you have to integrate it, and we'll do examples of that in class, all right? But there are a few simplifications, and the easiest simplification is this. There's something we would simplify. We would say we have 1d flux. If we have 1D flux, what we're saying is at our control surface, our velocity coming out looks like this. It is both constant and perpendicular to my interface. And if that's the case, then the integral of beta rho v dot n dA ends up just equaling the summation over my outlets of beta v a rho minus the summation over my inlets of beta v a rho. And if you want, you could put indices down here for each outlet and inlet you might have. But essentially, if you have 1D, you don't have to do the integral because beta rho and v dot n are all constant. V dot n would just be v. And so they pull out, and then you just get an integral with the area, and so it becomes the summation term.